Okay, good afternoon, or good morning, or good evening, wherever you are. I want to talk today about primary backup replication, and really sort of an introduction to primary backup replication. We'll come back to this in multiple lectures during the semester, but this is the FMT, the virtual memory or VMware fault tolerant paper is sort of a really nice introduction that brings out a lot of issues that are going to come up throughout the semester. So the plan for lecture today is as follows. I'm first going to talk about failures that you might hope to tolerate using primary backup replication, and some that you might not be able to. Then I want to talk a little bit about the main challenges in sort of any backup scheme, sort of broadly speaking. Then talk about two dominant approaches to replication. One is what's typically called state transfer replication, and the second is typically called replicated state machines. And today's paper is an example of a replicated state machine approach. And in fact, lab 2 over lab 3 and lab 4, also will be using replicated state machine approach. And in fact, the GFS paper for replicating chunks was using a replicated state machine approach. So it's quite a common approach. And then, I want to sort of make everything a little bit concrete by looking at this case study of the VMware fault tolerance scheme or implementation or system. So any questions before I get started? Just to put up, I have tried to answer all the questions that you sent by email. The ones that come in before midnight, I generally all answer. The ones that come in after midnight, I try to answer as many as I can. But if I didn't answer your question, then and the topic comes up in the lecture or at any point in time, feel free to interrupt and ask it. Okay, any questions before we dive in? Okay, so let's talk about failures in a very broad sense. To get a sense of what we might hope for that a replication scheme can handle. So first of all, typically the papers that we're in the system that we're going to be building will only deal with what's sometimes called or typically called fail-stop failures. And the basic idea is that if there's a failure or a component of the computer doesn't really work well, that actually stops the computer. So the assumption is that basically the computer goes from working to not working sort of instantaneously and doesn't produce weird results because the computer is not working correctly. So it just follows the protocols. When it does adds it to register values, that produces a correct add value, and so we're just assuming that when the computer works, it works correctly, and when there's a failure, it just stops. And this covers many scenarios. For example, whatever the fan of the computer fails, the computer overheats, and then the computer shuts down itself. The other cases are where somebody steps over the power cord and boom, the whole computer disappears, or cuts the network link, and at that point the computer might keep running, but it is completely disconnected. Sometimes systems or software on the computer itself does its best to turn these partial failures into fail-stop failures. So, for example, you might, the software might compute checksums on data, and then if it sees that the checksum is incorrect, just stop, the computer. And so that's quite common to do. So, but the basic model of the world is computer works correctly, then the computer stops. So what does this exclude? There's a whole bunch of sort of failures that it excludes. For example, it doesn't really deal well with logic bugs. So like if you have an error in your software, whatever, you divide by 0 and then incorrectly or in where you shouldn't have, then no, it is very likely that the backup will do exactly the same thing because the software is just broken, and so it's broken on the primary, it's broken on the backup, and so nothing, basically replication really does not solve that problem for you. Similar, if you have configuration errors, primary backup is not going to solve that problem for you. If the files that specify the replica set are just incorrect, then the system will not work correctly. Similarly, we're not really in this class, we'll talk a little bit at the end of the semester, but we're not dealing with malicious errors. So we're not dealing with attackers that try to fake the protocol, run servers that send incorrect messages and try to sort of spoof the whole system. We're just not in consideration. So for most of the semester, we assume that the software works correctly, does not have logic bugs, there are no configuration errors, and the thing that we're focusing on is actually handling stop failures. There's some failures that sort of fall, that could be handled or may be handled with primary backup replication or not. And as an example, you might think about like an earthquake. If the primary and backup are physically separated in completely different parts, on different continents, or maybe different parts of the same continent, and now you might hope that you might have some hope that the backup could take over if the primary fails due to an earthquake. But some other primary replication schemes, this is not going to be the case. Where, for example, if the primary and the backup are in the same data center and the whole data center disappears, then sort of end of story. Okay, so hopefully that gives you a little bit of context of sort of the type of failures that we're trying to shoot for. Now, even with this sort of just focusing on stop failures, it turns out to be difficult to build fault-tolerant systems. And we're going to talk a little bit about sort of the general issues that will show up, if we're going to build a primary backup system. And we'll see concrete instances of these problems in the VM FT paper. So one challenge is, if a failure happens, has the primary actually failed? An issue here, that makes this challenging is that in a distributed systems, you can't tell the difference between a network partition and a machine failed. So it might be perfectly possible that the network, that the primary is still up, but that some computers cannot talk to the primary because the network has partitioned. And so, for example, the backup might decide that the primary is dead because the network's partitioned, but in fact the primary is not dead. And maybe some of the clients are still able to talk to the primary. And so you have to have some story of making sure that you don't end up in a situation where you have two primaries. And again, we talked a little bit about last time. It shows up in this paper again. It will show up next week too, which is like, we want to avoid that we get into a situation where there's sort of a split brain system, where we basically have two primaries, and like one subset of the client talks to one primary and the other subset of the client talks to the other primary. And clearly that's going to diverge the state of the system, and when the network heals, we are in an incorrect state. And so we have to avoid this at all costs. The second general challenge is, how do we keep the primary and the backup in sync? Our goal is going to be that if the primary fails, then we can just gracefully fail over to the backup, and the backup just picks up right where the primary left off. And that requires that the backup actually is up to date with like the latest things that the primary actually has written to its state, so that it actually can pick up seamlessly and don't return errors or responses to the client that are completely unexpected. From the client's perspective, it really should look like, the whole thing, even though it's replicated, it's like a single computer. It just happens to be a little bit more fault tolerant than a single computer. And that turns out to be difficult. First of all, you have to make sure that we apply all changes. We have to apply the changes in the right order. And a continuous issue in that is that we have to sort of avoid non-determinism, or we have to deal with non-determinism. I mean, if the same change on the primary behaves different than on the backup, because for some reason that would be not good. That we got to make sure that we make a change on the primary and the backup, there are identical effects to the primary and the backup. A similar sort of issue that always shows up as a challenge is failover. If actually the primary fails and we need to fail over to the backup, we of course got to make sure that the other primary is definitely dead. But for example, the primary was in the middle of an operation and it was about to send a packet out to the response to the client, or maybe not. And so we got to figure out whether that response is being sent or not being sent, or is it okay for us to send it okay. There's a question here in the chat, like when would failover need to happen? That would failover need to happen when the primary is gone, right? Because then we want to fail over to the backup. That's sort of the terminology used. And then often another issue with failover is like who actually has to, we have multiple backups, which is not the case in today's paper. Who actually has the latest state? Like for example, maybe they all crash after a few operations. They come back up, and we are going to make sure that we're actually talking to the one that actually the most recent state. This is going to be not an issue today so much, as we'll see in a second why, but it will come up later in other replication protocols. Yeah, so basically failover means the backup takes over. Okay, so that's sort of the main the type of failures that we hope to handle, the main challenges, and we'll deepen those challenges out as we go. And I want to talk about sort of the two main approaches that we'll see in the semester for dealing with primary backup replication. One is, as I mentioned earlier, that is state transfer. The idea is reasonable at a high level, very straightforward. We got a primary. The clients talk to the primary. The primary, updates its state, updates the state in response to client request, and then once in a while it sort of makes a checkpoint. Once in a while, basically, it checkpoints its state. Its state to the backup. And of course, if we want the backup and the primary to be in sync, that means that every time the primary actually performs an operation before it responds to the client, it basically has to transfer whatever state changes that were made by that operation to the backup. So that's one scheme, one high-level approach. The second approach is what is called replicated state machine. State machine replication, often shortened to RSM. And here, the picture is, we still got the primary, we got the client talking to the primary, and of course, we have the primary talking to the backup to keep the backup in sync. But instead of sending the state changes or the modifications to the state from the primary to the backup, what we do actually, we send the operations to the backup. So before the primary responds to the client, executing its operation, we sent the operation that the client sent to us, to the backup, so the backup can execute the operation too, updates its state, acknowledges it to the primary. Primary actually updates its state too, executes the operation, and then sends the response back to the client. And sort of in all these in all these, in both approaches, the scheme is like the primary is in some particular state. We apply changes to the state, and we do it exactly the same thing at the backup. So the backup starts out in the same state as the primary. We apply the same changes to the state, whether it's through an operation or a state transfer. We end up in a new state, and that state has to be identical to the state that the primary has. And so if then ever there's a failure, we know that when we fail over to the backup, it is exactly in the same state as the primary, and so it can take over. And we'll see, this is actually challenging to actually make happen, but that's sort of the basic plan. The primary, both approaches actually reasonably popular. The primary disadvantage of the state transfer approach is that, like, if an operation generates a lot of state, then it's going to be expensive, right? Like if for a single operation writes a gigabyte of data, then that gigabyte of data needs to be transferred to the primary or to the backup. And it might be much more expensive, less expensive to basically just send over the operation to the backup so that the backup can execute the operation. So many of the systems that we're talking about actually therefore follow the second approach, where they send the operation but not the state transfer. And in fact, if you think about GFS, the discussion from last week, and we just saw that basically the primary sends the append operations or the write operations to the backups. It doesn't do the append and then send the result, to the backups. It actually sends the operations. So that's an example of a replicated state machine approach, where we'll be sending operations. And the paper of today also follows this replicated state machine approach, where the operations are not, append and write, file system append to file system write, but the operations are actually x86 instructions. That's what we'll see later. But they both, send operations. In labs, as I mentioned earlier, labs 3 and 4 are also replicated state machine approaches, where we're going to be sending operations from the primary to the backup. As a because there's a question in the chat, why does the client not need to send the data to the backup in our replicated state machine? Because the idea is that these operations are deterministic, and so the primary in this, remember the primary. We'll talk about this in much more detail, but the primary and the backup are in the same state S. If the operation is deterministic and you apply it to the same state, they will end up in the same state S prime. And so there's no reason for the client to send the data in this case, because by just sending this deterministic operation, it is guaranteed that that operation will generate the same data. So subsequent question is, how do you know for all programs and their operations whether they are deterministic or non-deterministic to know what information need to be sent? So the typical approach is in replicated state machine approach is to make all operations deterministic. Non-deterministic operations are not allowed, and we'll see in a second how you do that. Okay, so before going to a little bit more specific, are there hybrid approaches? Yes, there are hybrid approaches. For example, you can run sort of by default in a replicated state machine approach. In fact, in some ways, the paper does this. Then if the backup fails or primary fails and you go back to a single machine, then you need to create a new replica. And often for the new replica, the way you do it is actually by transferring the state from the existing replica or a copy of the state of the existing replica to a new replica. But that's like hopefully a less frequent operation. And then actually, doing then replicating the operations that they're doing much more frequently. Also, feel free to ask the questions, in real time as opposed to chatting, typing them in the chat. Either way is fine. But okay, so as I hinted, with this replicated state machine approach, there's a question about what level of replication you're doing, or what level of operations to replicate. So one possibility is sort of application level operations. And so what I mean is, think back at GFS, like whether it's append, file append, or write. Another, and if you play that game, sort of a replicate state machine game, at the level of the sort of application level operations, that means that the application has to be involved, because it knows what the semantics of these operations are. And it knows what an append actually is supposed to do, or what a write is supposed to do. And so if you're playing the replicate state machine approach at that kind of application level, then the application itself needs to be modified, to actually perform or play part of the replicated state machine approach. One thing that's cool about the paper today that we're looking at today is it does the operations at the machine level, or the processor level, or the computer level, and so the state is registers, the x86 registers, the memory state, and the operations are just ordinary computer instructions. And by replicating at that level, then you can basically make replication completely transparent, because you can take one computer, run the application or an operating system on top of it that just runs x86 instructions, and this replicated state machine approach automatically creates a backup of that particular execution. So the application doesn't have to be modified at all. In fact, in this paper, the operating system is not modified, the application is not modified. You can take an ordinary application, not even written with fault tolerance in mind, and using this sort of machine level or instruction level replication, it can be transparently replicated. So one of the things that is very cool about the paper of today is it's just completely transparent. Now, that makes you wonder, how to do that, because what happens if you have a machine and an interrupt happens? That interrupt needs to be propagated in some way directly to the backup, because if you think about an x86 machine, of course the regular instructions that the applications execute, like add, whatever, divide, conditional branching, procedure calls, but there are also other events like interrupts, and they need to be handled with. And so how do you do that? And so the traditional way of doing sort of machine level replication used to be sort of quite expensive, in the sense that you could buy computers where the processors maybe replicated twice or 3 times, and the hardware itself would organize that these processors ran exactly in lockstep. And that there's a lot of hardware machinery to actually make this happen. And this paper has a cool observation that you don't really need to do really hardware replication. Instead, you can actually use virtual machines. And that's the way they do it. Now, pure hardware replication happens too. For example, in aeronautics, or whatever, Mars rover, often the hardware modules are just double duplex replicated or triple replicated, and they have a hardware voting scheme, to keep sort of the processors in sync and to detect failures. But a sort of a level of fault tolerance that that is not what the level of fault tolerance that this VMFT paper is not actually shooting for. It's really thinking about you got a business application running on the computer, and now you want to make that business application more fault tolerant. And the approach to take is to exploit virtualization. So that gets me to VMFT and exploit virtualization. That's the main big idea that they bring down to this problem. And by doing so, they can make this replication transparent to the application. So you don't have to design as an application design and then replication scheme, for example, the way it's done in GFS. It appears, using the scheme, this replication scheme that the VMFT uses, it appears basically that it appears to a client that the service is a single machine. Meaning it just, we'll see in a second how, but basically they're going to provide very strong consistency. The client on the outside can't even tell. And it actually, the paper is sort of a cool paper because it actually it's a real product. And it's still in use. You can, get this this support if you want to. The current product, I think, is quite different from the one that we actually read about in the paper. But at a very high level, the issues are very similar. In fact, one of the big shortcomings, as many of you noted in the questions, of the one that's described in the paper, it's a single core solution. So there's no multi-core support. So multiple multiple threads on one computer cannot run in parallel. And we'll talk about in a second why the solution doesn't really support that. In the, I think, later versions of FT, this actually works, and I think there's no real detailed paper that describes it. But I actually think that instead of using actually replicated state machine approach, they're actually using a state transfer approach. But I really don't know any really of the details. I'm going to focus on the replicated state machine approach because one reason I like this paper is because it sort of illustrates the replicated state machine approach in a very clean manner. And all of the subsequent replication schemes that we're going to be looking at are replicated state machine approaches. Okay, so let us sketch out the overview of this system. And so the first thing that you sort of need to realize is that there's a virtual machine monitor involved. And so what is a virtual machine monitor? Well, a virtual machine monitor basically takes a piece of hardware and makes it appear, basically makes end pieces of hardware out of it. So if we have an x86 box, we can take a virtual machine monitor, run it on top of it. And on top of it, we can have virtual machines. And virtual machine, we can have multiple virtual machines. Although in most of this paper, we're going to be talking about running one virtual machine on top of the virtual machine monitor. And so, for example, we might actually have a Linux, operating system running on top of the virtual machine, with its, applications. And here's actually the actual hardware. And why, so the VM, the terminology used here is sometimes called a hypervisor. It's called a virtual machine monitor. And so in our case, really with the hypervisor here, this is actually VMFT. So it's a hypervisor modified, to include, the ideas that VMFT has. And why is this cool? Well, the reason this is cool or useful for replicated state machines is because if a hardware, interrupt actually happens, that hardware interrupt doesn't really go straight, to Linux. In fact, the hardware interrupt goes first through the VM monitor. And the VM monitor actually decides, when to deliver, that interrupt, to Linux. And so any external events, before they actually sort of observed, by the virtual machine, are actually captured by, or can be captured by the hypervisor. And so this gets us sort of out this mess, of like what I mentioned a little bit earlier, where, what happens if there's an external interrupt? How can we sort of replicate that? And the way we can replicate it here is because the virtual machine monitor just gets control over it. And we'll see, this is going to be an extremely powerful tool to actually make instructions deterministic, handle external operations, et cetera, et cetera. So the basic plan is if an interrupt comes in, whether it is an interrupt from the network or from the hardware itself, like a timer interrupt, basically the timer interrupt is delivered, to the virtual machine monitor. The virtual machine monitor, then in the case of FMNT, does two things. Not only delivers it at some point to the application, it also sends it over a logging channel to a backup computer. And the backup computer is constructed in the same way. It has hardware, it has the virtual machine monitor sitting on top of it. So here's another copy of FMFT. And on top of it, there's a virtual machine, where identical software running on it, like Linux, same version of Linux, with whatever, some set of applications. Okay. And so these machines sit both on some network. So here's the logging channel, and maybe here's a client, talking basically to the hardware to sends a packet over the network. The actual hardware receives that packet, and then they will deliver it, and the virtual machine monitor just gets control and delivers it, and the hardware delivers it to the virtual machine monitor, or the virtual machine monitor, if you will, picks it up. And so if you think about it, this packet results in an interrupt that's delivered to the virtual machine monitor. The virtual machine monitor will send that interrupt, as we'll see in a second, forward it to the backup. It delivers it also to the local virtual machine. The local virtual machine, there's just Linux running, and says, oh, I got an interrupt. And so it does its normal processing it always would do in an interrupt. And so at some point, maybe it will generate a response. And it will say, for example, write, to the network card, or at least it will think it's writing to the network interface card. But really what it is a virtual network interface card that is like emulated, by the virtual machine monitor. So when it writes actually, a bunch of instructions to this, virtual card, really what it is actually writing to the virtual machine monitor. And so the virtual machine monitor sees like, here's an operating system trying to actually send a packet. And then, the virtual machine monitor, can actually send the packet on behalf of the operating system by programming the real hardware. And then the real hardware, sends off, a response to the client. All right. So that's the sort of normal execution for what here's the primary, and here's our backup. And basically, at the backup, the same thing happens. If the machine started exactly in the same state, they take the interrupt, at the same time, and the virtual machine monitor can control when to deliver the interrupt. So it can arrange, to make sure that the interrupt is actually delivered exactly at the same time, exactly at the same instruction that the primary got it. So we'll deliver the interrupt, to the, we'll receive the interrupt from the primary, maybe buffer it for a little while until the backup, as we'll see in a second, hits sort of the same instruction that the primary does, then delivers the interrupt, to Linux. Linux does its usual way. It will be, since it's exactly in the same state as in the primary, it will do exactly the same thing as the primary does. So at some point, it will, program the virtual network card to actually send a response packet. All that stuff will happen. And at some point it says like, send that packet, the virtual machine monitor will get control. It knows it's a backup. And so it doesn't do anything. It actually doesn't send the packet on the network because it's the backup. Okay. So that's sort of the basic plan. Then there's one more component in this story that is important to realize, which is that there is on the site, on the same network, there is a storage server. You can think about this as sort of the hard disk, for these two virtual machines, or for the and so when an application, here writes to a file, really what it turns into is, the kernel will, that file system is maybe mounted on the local Linux operating system. The Linux operating system sees, this is like a remote disk, and we'll format the packet, and then we'll send that packet, to, let me draw it maybe in a slightly different. We'll send a packet, to the virtual machine monitor. Let's say place, the virtual machine monitor, like send it off. The virtual machine monitor, will go off and send it over the network, to the storage server. And the storage server will respond at some point. And in some ways, this communication looks identical as if there's like a client sitting on the other side of the network. The only difference being that in the storage server case, the Linux sort of starts the communication, while in the other case, the client starts the communication. Green arrows represent communication to the storage server. So a network packet being sent from through Linux, through the virtual machine monitor to the storage server. And so when so a write by an application to a file basically results in these messages, and then it will update any state, persistent state that on the storage server. Now, as we saw in the paper, the storage server plays an additional role on top of basically being a storage server. Namely, there's sort of a special flag that sits on the site, or there's a block in the storage server that's being used to arbitrate who becomes the primary after a failure. So and this all comes down to this is the part of the failover plan. So let's say the logging channel breaks, and the way this manifests to the virtual machine monitor is that it sends periodically packets over this logging channel, and if it doesn't get any responses from the other site, then it assumes that the other side there's a problem, and of course it can't decide whether just the network is not working or whether actually the virtual machine monitor the computer's really crashed. And if it's really crashed, of course it should take over. And if it's really not crashed, then we have to arbitrate in some way. We'll make sure that only one of them actually proceeds. So let's say the network partitions. And so this is the harder case when the network partitions instead of like one of them two crashes. So here, network partitions, but notice that the two can still communicate. Both the primary and the backup can communicate to the storage server. And so in this particular case, what will happen is they will notice, both sides will notice, the primary and the backup will notice, there's some problem. I can't talk to the primary anymore, or vice versa. And so they at some point decide, well, the other guy could be dead, and I want to promote myself to primary. So the backup says, like, I want to promote myself to primary, or the primary says, like, well, I just want to really continue serving client requests, and I just want to ignore the backup from now on. And so basically this says, this is what they want to go live. Basically go back into single mode, and we've one primary. And so the way that this happens is that both of them try to read. They call this a test and set operation. And I'll talk a little bit about it in more detail. But both reach out to the storage server and try to write a flag saying set it to 1. And if the flag was already set to 1, then it meant like that the other guy won or was earlier. Okay, so it goes from 0 to 1. They both try to do this atomically. One of them is going to go first. That will succeed. Setting to 1, and will get returned the old value 0. So it knows that nobody else succeeded actually in writing the flag to 1 yet, and therefore I should become the primary to keep it running. And the second guy, what's the primary or the backup, that comes in second, we'll try to set the flag to 1. It's already set to 1. The return value will be 1 because that was the old value by the time it, did its test and set operation. And therefore it will decide, well, I'm just going to give up because, there's already somebody else who took over for me. And basically, as the paper calls it, it terminates itself. Okay. So that's sort of the high-level operation, the high-level operation for failover. There's a question in the chat, which is a good question. When is the flag reset to 0? Well, there's sort of basically a whole separate story that I haven't talked about yet, and we'll see if we get to, is that once the primary runs on, we have one server running now. We'd like to make a second backup, and sort of get in the position that we're basically half a backup again. We have to do what's called repair, because if we don't do repair, then we start every 2 computers, one fails, then we have 1 computer, and a little bit later that 1 computer may fail, and then we have no computers anymore. And so it has to be the case. There has to be sort of a repair plan. And in VMVT, this repair plan is executed manually. So somebody monitors this, or the monitor software sort of notices this and basically creates then a new replica or based on the VM image of the first one, ensures that it's in sync, and then it resets that flag, and it's logging starts again, and then the flag is reset. So once that second primary is completely back up and following the protocol, then the flag can be reset. Okay. Okay. Okay, good. That's a great question. Like, why maybe the logging channel broke, but maybe the channel to the server broke too, and so we're not going to get the response. And that basically, at that point, the system just stops, if you will, until something repairs, because nothing can be done. So at that point, from then on, no client requests are actually processed because we just don't know what state we are. And maybe at some point the network link will get repaired, and endpoint, things start moving forward again. And so that's sort of the disaster case, right? Where disaster case is actually the primary and backup are both actually up and running, but all the network cables are broken. And which is sort of similar basically to the case where both the primary and backup failed at the same time. Okay.
Question.
Yeah.
Could you explain again real quick when the client is reading from the storage server?
The client never reads really from the storage server. That's the Linux that might, or the application running on top of Linux might be running from the storage server. And that's the one case. In the second case, VMFT might be running from the storage server to read that flag or test and set that flag.
So that like green arrow at the bottom from the storage server to C is
sorry, that green that's a bad green arrow. That should have gone like all the way.
Oh, okay. Thank you.
It's just going over the network and not intended to go to C. It was intended to go over the network. Thanks for clarifying that. Hadn't realized that. Okay, so so what I like, so I want to maybe take a quick break at this point, or do a breakout room. In particular, what I'd like you to do is talk a little bit about the homework question, which we sort of covered at this instance. But I want you to think about, like, understand or argue with each other, and convince yourself that the scheme actually avoids this sort of split brain syndrome, in the sense that there's never going to be two primaries. And the second thing, maybe to debate is this a reasonable design? Because it looks like, what we've done is like we pushed all the sort of real hard part of the fault tolerance into the storage server. And is that really the case, or is that not the case? So that seems like two things that I'd like you to discuss in these breakout rooms. So I'm going to stop the sharing. And I'm going to participants, and I'm going to make Lily host so that she can set up the breakout rooms and enjoy talking to each other. Lily, you got this under control?
testing to see if I can join a different room this time. It's not looking good though.
Well, I guess I'm stuck here.
My screen again. Can everybody see the screen?
Yes.
Okay, good. So I hope you had a good discussion and hopefully met some more new students in the class than you knew before. And let's sort of proceed talking a little bit about the design of VMPT, and just summarize quickly, this.
Sorry, could you repeat like when the flag is reset to 0? I feel like some of us might have missed the explanation.
Okay. Okay. So good. Okay. So here, let's draw the picture again in a sort of simpler way. Here's our primary with the VM, everything in it. Here's the backup with everything in it, and there's the logging channel in between. They're connected, to a storage server. And one thing to think about is that the storage server is playing two roles. So let's separate the two roles. One is the storage, for a disk basically for the primary and the backup. And then we can just split that and just attach the disk to the primary and the backup. And then we basically have the role here is really the arbitration server. and it has a flag, and the flag is initially 0, right? And so now let's say there's a partition, the primary and the backup can actually not talk to each other anymore, so they're going to talk to the arbitration server basically to try to promote themselves through the single to go live and sort of to be the single server that serves the client request. So they both send the packet to do a test and set operation. One gets a 0 back, the other one gets a 1 back. The one that gets a 1 back knows that it was actually the second who tried, and then and so the first one will succeed and will go live. So let's say this guy goes live, and this guy just disappears. This virtual machine terminates itself and is done. And so now the flag is set to 1. And of course, now at this point, there's no arbitration necessary anymore because there's no secondary replica. There's no backup at all. So really the question is like, what happens next? And in terms of repair, that has to be the case that the second backup, a new backup is brought up to life, correct? And section 3.1 of the paper talks about this in quite a bit of detail. And the way it works is that, on the user interface, to the system, VMware Motion, you basically say like, hey, I want to clone this primary. And the cloning operation basically will basically stop processing client. During cloning, the primary won't actually, or the one system still running, won't actually serve any client request. The VM Motion thing makes a VM clone and basically copies, the state of this VM up to the backup. And so here we have an identical copy of the backup of the primary that becomes the backup. And so the state of the virtual machine is identical. Once the sort of this cloning operation has happened, then it's free. The user interface is free to set actually this guy back to 0.2. Client requests are still not being processed. When that has actually happened, then the system can go sort of live again, but now with 2 machines, with a primary and a backup. And then client requests are being processed. They're sent over the channel, et cetera, et cetera. So we're back in business. Does that answer the question? I hope it does. If not, I'm happy to revisit this actually maybe at the end of the lecture if it's still confusing. Okay. Okay, good. Okay, well, I want to go back now to sort of like the overall architecture correct of the system. Now I want to dive in a little bit more and talk. We have decided, I think, that this arbitration scheme allows you to at least avoid the split brain syndrome. But there's sort of just still this larger issue that if 2 machines are running, our goal is going to be basically behave like a single machine. So from the client perspective, it should not be possible to really discern, or at least in a sort of a demonstrable bad way, that we're actually having 2 machines. Great. And so just to take a step back, if we think it at a very high level, we have here our primary, and it has like machine registers, the virtual machine has registers, there's memory, and our basic plan is to sort of forward, make sure that basically they execute exactly the same instructions. Boom, boom, boom. Here's our own. Here's our backup. Here's our primary. And basically, when the when the primary, so we start them out in the same state, and they start executing instructions. So like maybe the first instruction is in ink, the second instruction is in deck. Third instruction is a branch. And if they start all in the same state, correct? Then at the first instruction is branch, then we'll branch in the same direction. And so maybe the branch do some instruction n, and whatever the next instruction is in divide, et cetera, et cetera, et cetera. Now all these instructions are sort of deterministic, so they're pretty straightforward, right? Like if we both start at the same state, they execute exactly these the same set of instructions in the same order, then we're going to end up in a state S prime, and those two states are going to be identical, right? Now, the thing that is sort of the challenge in this design, or like any sort of replication scheme, is there might be sources of divergence. So our goal is to actually get them exactly to the same state S prime, but there are sort of sources of divergence. And it's pretty obvious, correct, that what those are. For example, instructions that are non-deterministic are a problem. And so what is an example of a non-deterministic instruction?
Getting the time,
Yeah, getting the time. Why is that non-deterministic?
because it depends on time. And the machines are not like the backup is not executing at the same time.
Yeah, the issue here, correct, is that if the primary and the backup, at some point they will execute this, get time of day instruction, if you will, and they might not execute it exactly at the same time. So the values returned, by that instruction is going to be different. Right, so that's a source of a potential source of divergence that we need to control. In fact, we basically have to turn every non-deterministic instruction into a deterministic instruction. And we'll see in a second in how could that be done. Similarly, inputs, right, or packet inputs, like when a packet arrives over the network, at the primary, we got to make sure that that packet is executed or processed, or the interrupt that goes along with that packet is exactly delivered at exactly the same point in the instruction stream, right? So we go back to our previous paper, the page, and the backup's also executing these instructions, and deck, blah, 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 exactly in the same order. So if the primary, for example, would get the interrupt is delivered between instruction 1 and 2, we got to make sure that at the backup, it also is delivered between 1 and 2. Because if it's delivered exactly in the same point in the instruction stream, then the interrupt handler will run, and it will, they both will execute the same instructions again. However, if, for example, the backup, would process, this timer interrupt, or this packet arrival interrupt, and a little bit later in a different side of the stream, then the state of the system might be different, and therefore the result of that, computation might be different. And so we can't have that. So it has to be the case that interrupts, whether it's packets or timers, all get delivered exactly at the same time. And the same put in the instruction stream. So input, packets, or timer interrupts need to basically be delivered at the same point in the instruction stream. And so those are the sources of divergence that we need to handle. Any other sources of divergence that
so I think it was mentioned in the paper that concurrency also can produce non-determinism. But from my understanding here, since the hypervisor actually controls the interrupts, and since we have a uniprocessor, wouldn't the thread switch be conducted through the hypervisor by interrupts? So if we control the interrupts and we can transmit them exactly at the right location, wouldn't we also control the non-determinism from concurrency?
Yeah, so I think there's a great observation. So it's a potential divorce. Okay, so first of all, let's first agree that it's a potential source of divergence. So multi-core. And let's say, and basically the way the solution in this particular paper to avoid this problem is to say well, just disallow. We're not allowed to have that. And so just only uniprocessors. But let's say we had multi-core. And just to make sure that we understand what the issue is, the issue here is correct. We have 2 threads running on the same processor, but on different cores, and they race, for example, to grab a lock, and one of them is going to win, and so that's the thread that's going to run next, and the other one is going to be stopped for a little while. If we want to do this replicated state machine approach at the backup, the same thing would have to happen, right? Where if the 2 threads run, race for that lock at the same time, then we got to be arranged that whatever winner on the primary is also the winner on the backup. And so that requires a whole bunch of machinery, additional machinery or complexities that the paper clearly didn't want to address or didn't know how to address. And basically just said okay, we're just going to exclude that possibility of divergence by just declaring that the processor is a uniprocessor. And so then thread switching and all that kind of stuff doesn't matter anymore. There's always one computation running on the computer, on the processor, and it will switch. If the primary switches to a different thread, the backup will switch also to the same different thread, because it's like a single instruction stream, and they get their external inputs exactly at the same time. Does that make sense? So in some ways, it's a little bit lame. They just give up on multi-core. And as I mentioned, later systems, the more recent systems of this product do handle multi-core. And you know, I don't have time to. I don't actually understand exactly how they do it. There's a potential different schemes that you could think of doing. You know, people have done multi-core replay, which is really what's the thing that is necessary. And so, but I don't really know exactly. So I'm not going to talk about that at all. I'm just going to talk about that, focus on the first 3 items and see how they handle it in this case. Okay. Any questions?
Sorry, just to make sure, it only transmits the instructions that the application makes, right? It doesn't transmit the instructions that Linux makes.
Yeah, exactly. So here's an interesting thing. We'll see in a second, but let me make that more clear right away. In fact, these instructions inc and dec and branch are not sent to the primary backup at all. They basically have their own copy, correct? And we're just starting them at the same point in the program, and so therefore they run exactly in a sort of lockstep almost. Well, they don't run in lockstep, but they execute them in the same order. Only something special has to happen at these points of possible divergence. And you know, the assumption that sort of the paper makes is that most instructions are deterministic, so we don't really have to do anything. It's only at the instructions where things are going to potentially go wrong, we have to do something. And so one of those sources where something could go wrong is interrupts. So let's talk a little bit about interrupts. And so here, like basically the virtual machine sort of comes to rescue and really helps us solve this problem. So let's say here we have our hypervisor. An interrupt happens. Now the interrupt will show up at the hypervisor, and the hypervisor knows exactly at what instruction the application was, or the VM was at this level. So here Linux is running inside of this VM. The interrupt happens. Of course, the hypervisor already has taken over control, and it knows where it stopped. Linux to actually take the interrupt. So maybe whatever it took it at. It has executed 100 instructions so far. And then, this interrupt comes in, and the hypervisor now wants to deliver that interrupt basically at instruction 100. And before doing that, actually, it just sends over the logging channel a message, to the backup. Okay, so here's the backup, FT, and in that message, it basically says like, okay, at instruction 100, when you get to instruction 100, deliver this interrupt. And maybe some data that's associated with the interrupt. Right, so this does 2 things. And the interrupt comes in, sees what the instruction number was, and then it sends to the backup this message saying like, hey, at some point, when you get to instruction 100, process, this interrupt. And some point later, there's interrupt 1, and interrupt 2 comes in. And so the hypervisor does exactly the same thing. Again, we'll send out a say this is at instruction 200. We send the message 200 interrupt. Perhaps for any data associated with the interrupt, to the FT. So when the backup gets the first message, it just buffers the message because it doesn't know how long it can run after that message until it knows what the next point is that it has to deliver something. So at the point that the second message comes in, for the second interrupt, it knows, it's perfectly fine to start the computer at instruction 100, deliver the interrupt, and basically keep running until instruction 200. And the way it does it is there's basically, most processors have this, but x86 has this too, where you can basically program the x86 and to say like, well, you should stop after executing 100 instructions. And so the processor will stop executing after 100 instructions and just give back control to the operating system, or in this case, the virtual machine monitor. And so, and so this is the scheme. This is the scheme that the VMFT uses to basically, deliver interrupts both at the primary and the backup exactly at the same instruction, so that they sort of stay in this exactly execute the instructions in exactly the same order. To arrange this, of course, the backup needs to lag behind one message. Okay.
So just to be clear, so the deterministic operations don't get communicated through the logging channel. It's only the operations that perhaps might diverge. The
Exactly.
execution.
You got it. That's exactly what it does. So let's look at one more, just to get the flavor, and then we'll talk about it. Yeah, go ahead.
Sorry. So deterministic operations, you said don't get communicated through the logging channel?
Nope, there's no need for them. Because, because both of them, of course, have a copy of all the instructions of like the binary that like whatever Linux runs, correct? But the instructions are not communicated over the logging channel. It's only the non-deterministic ones. So like this interrupt, and we'll see in a second. Here, let's talk about the second one, non-deterministic instructions. Like get the timer, get time of day. So the way that works is. So here's we got our Linux running in the VM, we got our FT running, and basically when this Linux, so here's sort of the image, the program image that Linux runs, and maybe here's our non-deterministic instruction. And basically what FT has done before it started Linux, it's sort of gone through like the Linux binary and found all the instructions that are non-deterministic, like get time of day. And basically ensure, turn them in sort of an invalid instruction. And so when Linux executes that non-deterministic instruction, it actually transfers control to the hypervisor. This is the trap. And now the hypervisor knows, okay, well, this was, whatever, instruction 341. I know that is a non-deterministic instruction because I wrote, those bits, that caused the trap. And it will emulate, that instruction. And so it will do all the effects that instruction has, but record what the results of the effects are. So, for example, whatever, and we'll record what the result, executes the instruction, the result goes into A0, it records the value of the A0, and then basically sends to the backup, the outcome, of that instruction. So whatever is like, if the value in A0 is, whatever, 221, then it will, send back, saying, there's non-deterministic instruction. The result of it is 221. And at some point, correct, since the backup lags behind, it will, execute, because it's executing the instructions in the same order, in the same way, it will also execute the non-deterministic instruction. That will trap into the kernel. And now usually we'll wait until, since it lags behind, it already has received probably the message, and basically make sure that, it sticks the same value, or returns the same value as it did on the primary. Right? So this is how non-deterministic instructions are handled.
Sorry, so that happens, like the modification of the binary, it happens when it creates the virtual machine?
Yeah, we think about it when it boots the VM.
Oh, okay.
Wait, so the backup re-executes the non-deterministic instruction and then just verifies the result?
No, what it actually does is if the virtual machine monitor executes the instruction, and then, or actually the virtual machine monitor doesn't execute the instruction at all, it knows that this instruction needs to be executed, and it knows what things will be changed, like what registers need to be updated as a result of this instruction, and it sticks the value from the message into the right register so that the the Linux running on the backup sees exactly the same effect as the Linux running on the primary.
And so like this assumes that the hypervisor will do some work before even or while booting up the VM, just
Yes.
to know where the locations of these non-deterministic.
Yeah. Which any hypervisor does these days.
Okay, I see.
So this is sort of standard hypervisor stuff. This is nothing new to FT, other than these guys have a ton of experience doing hypervisors, correct? Because of VMware, and so they understand like what it takes, and which instructions are non-deterministic.
Mm-hmm. Thank you.
Okay, so
I had one more question. So if it's a program of fully like deterministic instructions, could the backup run faster than the primary?
Okay, so there's a whole discussion in the paper about like the speed of the primary and the backup, and making sure that they run roughly at the same speed, because you don't want to get one far ahead and one not far behind. I think you should think about them. They're running on sort of identical hardware, and so they run roughly at the same speed. It's also the case that there's going to be always some communication over this channel because interrupts happen periodically, right? Like every whatever couple milliseconds, or maybe 100 milliseconds or tens of milliseconds, depending on like how Linux and what rate Linux programmed the hardware timer. There will be a timer interrupt, and that timer interrupt will be propagated, to the backup and sort of be a sync point, if you will.
Right, but my question is like, for example, say you have a bunch of like deterministic instructions, right? Instructions that aren't sent through the logging channel.
Yeah.
Which means, the primary and backup can run those instructions at their own pace, correct?
Yes.
So say, I mean, I don't know if this could happen, but say like, it's 100 instructions, and the primary goes to like instruction 50 and gets a timer interrupt, but the backup is already a timer like 60 or something. Could that like?
No, could not happen, correct? Because remember, the backup lags behind one of these messages. So the backup won't start executing the next block until the primary already has finished it.
Okay.
And this is why it lags behind one. Exactly for that reason.
Like to ensure that the backup is like lagging behind one instruction. Does that mean you have
No,
to?
not one instruction, one message on the channel.
But the interrupt is unexpected, right? So if we have, as he said, if you have 100 lines of instructions and running on the backup as well as on the primary, then
the backup would not have started yet, right? So the primary runs the 100 instructions. The backup actually waits until the primary actually has completed, whatever those 100 instructions before it starts running those 100 instructions. So just, one way to think about it is like always runs like one epoch behind.
Oh, so it's kind of a batching kind of scheme.
Yep.
All right, thank you.
Okay, so I want to talk a little bit about failover because there's there's one more rule that needs to be ensured that we actually get the right behavior. And so let's walk through some scenarios. Here's the primary. Here's our hypervisor, right? FT. Here's our logging channel. Here's FT. The both sit in the network. Here's the client. And here's our backup. And I'm going to talk about a couple sort of scenarios. So the first scenario is sort of the normal case, or the client sends a message to the primary, or like the server is running on the primary, that's delivered, of course, to the primary. It's also sent, to on the channel. And let's assume for a second that actually the message, arrives, at the hypervisor. So it actually knows that this was an interrupt and some packet arrived. And so now let's say the primary sends a response back. And at that point, the computer crashes. So if the primary fails, the client has not gotten a response yet. This turns out to work out perfectly fine, right? Because before the backup actually takes over, it first processes all its messages that hasn't received yet, because it lags one behind, as we talked before. So this thing will be delivered. So it will. Sorry. Okay, let me be a little bit more careful. Okay, so it gets delivered, the prime backup does it, but it actually won't send any response because it's still sort of, doing exactly what the primary has done, gets to that particular point and stops. Then point, they erase, or like the backup actually becomes the primary, through the arbitration server, and the client will just time out and retry, right? Because like TCP packet didn't get a response, so it will retry. So everything works out perfect. The interesting case is what happens in the following scenario, where the client sends the request, it arrives at the primary does the operation or whatever process the client requests, sends the message to the fault-tolerant server. In the meantime, okay, it was also sent on the logging channel, but let's say we got unlucky. The message actually never made it over the logging channel. And but the primary actually, sends a response before and just sends a response, and then it fails. Right. And so, for example, like maybe, this request was like increase, the variable from 10, to 11. So inc, the old state was 10, and now the new state is 11. All right. And is this problematic, this scenario?
Yeah, because when the backup takes over, it won't know about that increase. And so it'll just continue execution as if it didn't happen. And this provides like inconsistent output to the external like facing world, I guess.
Yeah, exactly. Right. Because the primary will take over, the backup will take over, the value will still be 10. And now if the client does an inc, it actually gets 11 back instead of 10, or instead of 12. Right. And so this is no good. And so how is this avoided, this problem?
The primary will send things to the backup and then wait for acknowledgement. And once that acknowledgement is received, it can send output. And it doesn't matter whether the backup actually runs the command, it just has to like have it so that if it ever needs to take over as primary, it has that in its logs and it will catch up before actually like becoming the primary.
This is exactly right. And so this is what's called the output rule, right? And the rule is that, before you can output, you got to make sure that the preceding messages that you were sent to the backup actually have been received by the backup. And so the scenario that just drew out, can actually never happen because, at the point, the primary wants to send the response out on the network, the FT, the primary FT, will wait until this message actually has been received by the backup, and only when it receives an acknowledgement from the backup FT, and now it knows, that basically the backup has a copy of this input, and so whenever it fails, the backup will process that input and basically get the computer in the same state as in the primary. So at that point, it actually safe, to send out the reply. And so this is the output rule, is that you don't output until all preceding messages that you send over the log channel actually have been received by the backup.
And so just to clarify, it seems that the output rule is here to solve the inconsistency that could happen if we have some non-determinism. So like, let's say that we have the output operation to be instruction 60, and we did not have the output rule. And so the backup actually did not, let's say for some reason, did not receive the output operation, or it did not receive up until the output operation. If the instructions are deterministic between the point where the backup did not receive messages until the point where we have an output operation, do we still run into the problem of the inconsistency?
Yeah, because the client might have observed it, right? The client might have observed that actually the value is now 11. And so when it actually talks to the backup after the primary has failed, then the value is suddenly 10. And it's just like, can't be true. So that, that reveals that it's not behaving like a single system.
I see.
So it's really the external, it's the external thing, the external client that will observe something wrong. And this is why the output role exists. And any replication system that we'll see this semester has something like the output rule. It turns out to be, for example, we'll see in the, even in the RAF paper, but also in the Zookeeper, there's sort of this notion that, sometimes you want to like respond to reads immediately, but you can't really do that because you run this risk. And there's sort of an equivalent of an output rule that tries to avoid, problems like that.
So does the client re-execute the command? Like, do they get some sort of signal that, because the command was never acked by the backup?
Okay, okay. So let's say we did not get the ACK, right? So it got to the backup, but not to the ACK. Then the client will have not, this response would have not been sent to the client yet, correct? The backup will take over. The client presumably will time out and do whatever it needs to do. Either does nothing. If that's part of that's part of the protocol between the servers and the client. Most likely, the client will reset. Right? Like there's a TCP connection. the response packet didn't get received, and so it will, try to resend, and so it will resend to the backup, and then finish the operation. But it won't observe an old value. Okay. Okay. Now I want to talk on one thing a little bit. So this system, I think, is actually very cool. It's a very clean version of sort of state machine replication. It brings out these issues of non-determinism, the issues like the output rule that we'll see in versions of that we'll see in similar in other systems. But I want to talk a little bit about performance, because like one downside of this system is, because you're doing things at the level of the machine instructions or like at the level of interrupts, you pay a performance hit. And so like, I want to point to the two tables that are in the paper. And one, first thing to observe is that actually the left table is actually extremely good. So the backup and the primary, if you run the backup and primary, the performance is very close to as if you were not running with a backup, which is very, very impressive, including the fact that you're running a virtual machine. The more troublesome part is this side of the things, where if you don't run in a primary backup mode, like your bandwidth on receiving and sending actually is pretty high, at least in the particular experiment they did. But when you're running in the backup mode, things are actually not so good, right? These numbers are quite different. In fact, there's sort of like a 30% reduction in performance. And where is that 30% coming from? Well, like, why is that the case?
Is it because the primary is actually the one receiving inputs from outside?
Yeah, well, I think there's two cases. On the receiving case, right, the primary is receiving input from the outside, and where does that need to go? It receives a packet from the client, and so that packet has to be sent, to the backup. And furthermore,
right, but the primary is also the one sending output back to the clients. So is that what's using the bandwidth?
Well, that's one reason. That's what the bandwidth. That's part of the bandwidth using. But the real thing I think is going on here is that the primary has to wait until it can send a response to the client until the backup actually has acknowledged it. And so it just can't like process packets at the same speed as it could without actually a backup. And therefore, we sort of see a reduction in performance. Nevertheless, this performance is pretty impressive, but there is a performance cost, and this is one reason that people play this game of replicated state machines not at the instruction level, but at like the application level, and basically be able to get higher performance, but that requires modifications to the applications, as we saw in GFS. Okay, I think I'm running a little bit over time, so I'm going to stop right now. And I hope people that actually needed to leave already left, but I will stick around. So if people have more questions, I'll be happy to answer those. And I'll talk to you on Tuesday.
Thank you.
I had a question about the previous image that you drew with the that one. I was confused because wasn't it the case that if that number 10, it just sits in the memory, then when we do an increment, we don't need to send anything to the backup, right?
Okay, so there's two things going on here. So we do at the point that the message comes in, like this increment comes in from the client, arrives at the FT, at the primary hypervisor. It needs to forward that message to the backup FT so that it can process it if it needs to be processed, when it needs to be processed. When it processes exactly at the same point in its instruction stream, right? So it sends it off, and then delivers it to the primary, and then the primary goes up and does its thing. Primary may respond with a message, and so if the primary responds with a message, the output of that message is stopped or on hold until the backup has acknowledged the reception of this increment, which will ensure that if the backup has to take over, whatever, it will process that increment first, and it also will be 11 before a response is sent.
Okay. Okay, I think that makes sense. Thank you.
You're welcome.
One thing I was kind of confused about is the goal of the system to help with like backing up an actual server, where because it's not easy to handle the interrupts without a hypervisor, or is it actually to help distribute virtual machines themselves?
It is purely to make an app, like you have a business application that runs on a single machine, and you want to make it more fault tolerant. And what this scheme does is it makes it fault tolerant for you transparently. You run the business applications on both machines on the FT hypervisor, and the FT hypervisor will ensure that basically these applications more or less not literally running lockstep, but basically are fault tolerantly replicated.
So the VM, using the VM itself, is kind of a design decision.
Yes, and that is a good design decision because it allows you to do this sort of replication at a transparent level.
Got it. Thanks so much.
You're welcome. Yeah, there's the question in the chat about can the output rule, is it possible that the client sees the same response twice? And the answer is yes. It's absolutely possible that the client will see it get the response twice. And basically what they argue, that's okay, because in sort of the fault tolerant model of the network, it is always assumed that the network can actually duplicate messages anyway. And so protocols like TCP are totally designed to deal with duplicate messages. So yes, it's okay because of TCP or whatever replication duplication scheme the application uses or the client uses.
I was curious about Kat's question, which is if the primary sort of goes down for a few minutes, backup goes live, then sets up its own backup, switches the bit back to to 0, and then suddenly somehow the first primary goes back
Oh yeah, so it has to be the case that first primary is definitely terminated, cleaned up, and
okay.
gone.
Mm-hmm. Nice.
Yep.
Okay, thanks.
I was going to ask actually something similar. Maybe too broad of a question, but will you ever need to store more things besides an arbitration flag in the server, or besides a flag in the arbitration server? If you have multiple backups.
Oh yeah, if this is a scheme tailored to one backup and not more than one backup. So if you had more backups, there's other issues that we need to resolve. And in fact, we'll come back to this on Tuesday, with more sophisticated protocols that handle those cases much cleaner.
Okay. Okay. I was just okay, cool. Thank you.
I have one question about the performance.
Yeah.
So can you go back to that table? Yeah, so my question is it the delay only be viewed on the first packet? Like after the first packet, it will just flow through the channel and there is no extra delay on the link. So the bandwidth should be roughly the same, but no.
No, I guess for every packet received, correct, by the primary, that packet has to be forwarded to the backup.
Mm-hmm. Yeah.
And for every response, the backup will have to wait, or the primary has to wait until the output rule is satisfied, and then it can send the response.
Mm-hmm. So there is some processing on the backup server too before getting back to the primary.
Yeah, so again, they talk a little bit about that, correct? The particular processing that needs to be done is actually acknowledging the reception of the packet on the logging channel. And they talk a little bit about how to reduce the delay to make sure that sort of the acknowledgement is very quick.
I see. Okay, thank you.
You're welcome.
I have a question about the logging channel. So they mentioned that they use UDP, and I assume that's mostly for performance.
Mhm.
But then, so basically, if a single failure happens, the primary, like if a single packet is unacknowledged, then it assumes that the backup failed without
No.
any like retransmission.
No. Because of there's a timer interrupt, and the timer interrupt goes off like every 10 milliseconds or something. There's always sort of multiple, one packet is sent. If that packet doesn't get, there's no heartbeat coming back, then it will do a couple of these time interrupts before it gives up.
Okay, and the heartbeats, are they coming from the primary, or it was like sort of
No.
implied it was like from somewhere else in the system?
Well, they sort of come from the timer in. The heartbeats basically have an indirect side effect because every 10 milliseconds you're going to send an interrupt message to the over the logging channel anyway.
I see. Okay. All right. Thank you.
You're welcome.
Actually, I wanted to follow up on that. I think it said that it's gonna wait a few seconds to.
Yeah, it will wait a while. We'll do a couple heartbeats and wait a while, and if there are really none of them that go through, then it will stop.
Okay, and is a few seconds? That's a lot, right?
Yeah, I don't remember exactly all the numbers, so you could be right on the few seconds. I would imagine it's a little bit shorter, but maybe it's not. No,
It
clearly,
didn't say. I think it said like something in the order of a few seconds, but is it bad to wait too much?
That was for the cloning, but I can remember the right